Overview. Bleed air is supplied from the main engines or APU. Air is bled from each engine. Pressure and temperature are controlled before supplying aircraft systems. The APU is only capable of supplying a limited air supply. Engine air supply. This section describes the basic operation and components of the air supply system. Air supplies on each wing supply separate systems. Engines 1 and 2 supply the left side. Engines 3 and 4 the right side. A single engine on one side can support its own systems. Each engine has a similar layout. Hot air is supplied from the final compressor stage of each engine and fed into the pylon. Within the pylon there are a number of components to control the air supply and pressure, temperature and mass flow. Air supply and pressure are controlled by an isolation and pressure reducing valve, normally called the engine air valve. Each valve is controlled by a two-position switch on the air supply panel. This valve controls the supply of air and reduces its pressure to 41 psi for system use. The valve will close when the associated fire handle is pulled. The engine air valve is pneumatically actuated and requires air pressure to open. If the valve is not in the position selected, an amber engine air valve annunciator will illuminate. If engine air 1, 2 or 3 are selected on with the aircraft on the ground, a green air selected on ground annunciator will illuminate on the central status panel. There is no indication if engine air 4 is selected on. This allows engine air 4 to be used during takeoff if the APU is unserviceable. If the valve fails to control pressure correctly, an amber engine air fault annunciator will illuminate, and engine air valve will illuminate as the valve automatically closes. The temperature of the air supply is controlled automatically. Cold air from the bypass duct is regulated by a temperature control valve and passed through an air-to-air heat exchanger called a pre-cooler. This reduces the supply temperature to 200 degrees Celsius. A mechanically operated duct pressure relief valve will vent any excess pressure into the pylon area. There is no indication of relief valve operation. In the event of a duct failure downstream of the pylon, maximum bleed airflow is controlled by a fixed venturi. A non-return valve, check valve, prevents air from the adjacent engine from entering the system. From each pylon, air is supplied rearwards for airframe systems. A separate supply, controlled by an ice protection valve, provides hot air for wing ice protection. A supply upstream of the engine air valve in numbers 2 and 3 pylons only provides air for hydraulic tank and stall air pressurization. Air pressure is controlled to 50 psi by a regulating valve. Blowout panels are fitted in the pylon to relieve excess pressure caused by duct failure or relief valve operation. The regulated air supply for hydraulic tank pressurization is provided by number 2 engine for the yellow reservoir and by number 3 engine for the green reservoir. Either or both numbers 2 and 3 engines provide air for the stall air reservoir. What will protect the engine air bleed if there is a duct burst downstream of the pylon? Airframe systems. Air is distributed from the pylons to the left and right systems. How is the supply of air through the pylon controlled? A connection between the left and right systems via a shuttle valve allows an air supply to the water tank and the forward and rear discharge valves. Which air supplies can pressurize the potable water tank? The air supply to the discharge valves is used to keep them open when the aircraft is on the ground. This will be discussed further in the air conditioning and pressurization module. Bleed air is supplied to 2 air conditioning packs at the rear of the aircraft to provide pressurization and air conditioning. Ice protection for each wing is supplied by one or both engines on that wing. Air is supplied to the tail from both the left and right systems. The left system is used to provide air pressure for the flushing of the toilets. How can the green system hydraulic reservoir be pressurized with air if number 3 engine is shut down? APU air supply. The APU can be used to supply air for air conditioning, toilet flush, water tank pressurization, and the discharge valves. The APU cannot supply air to the hydraulic tanks or stall air reservoir. Why is the APU unable to supply air to pressurize the stall air reservoir and hydraulic tanks? Airframe ice protection cannot be supplied by the APU as it is unable to supply the volume of air required. When airframe ice protection is required, APU air must be selected off. APU air is controlled by a switch on the air supply panel. This switch controls the APU air valve. The air valve regulates the mass airflow to the air supply system to maintain a constant delivery pressure. If the APU air valve fails to close when APU air is selected off, APU valve not shut will illuminate on the air supplies panel. Non-return valves, check valves, prevent engine bleed air from entering the APU. A leak of either non-return valve with APU air selected off will illuminate APU non-return valve leak on the APU panel. External checks. Ensure that all 3 blowout panels on each pylon have not operated and are secure. Pre-flight. On completion of this section, you should be able to carry out the checks required to prepare the air supply system for flight. Before APU start, confirm that APU air is selected off and the APU valve not shut annunciator is out. After APU start, APU air may be selected on. A minimum of 1 minute after APU power available illuminates. Air conditioning can now be selected as required. Engine air must be checked off, and the associated engine air valve and engine air fault annunciators extinguished. If the APU generator is to be used to provide power for engine starting, the air conditioning packs 1 and 2 and APU air must be selected off to reduce the load on the APU. After engine start, air conditioning may be restored by switching APU air on and both packs on. Several factors must be considered before deciding the take-off bleed configuration. It is always desirable to provide air conditioning for passenger comfort during takeoff. Unserviceability or company policy may dictate whether the APU is available or not. If the APU is available, takeoff will be performed with APU air switched on to provide control to the discharge valves, and both packs selected on to provide air conditioning. Click on the yellow ellipse and set up the panel as above. If the APU is not available, we refer to the performance data to see if our desired takeoff weight is limited by having engine air selected on. If performance is limited, takeoff is performed with engine air 4 only selected on to provide control to the discharge valves. Click on the yellow ellipse and set up the panel as above. If performance is not limited, we must then consider if engine anti-ice is required. If engine anti-ice is required, takeoff is performed with engine air 4 only selected on. Takeoff is not permitted with engine bleeds on and engine anti-ice selected on. Click on the yellow ellipse and set up the panel as above. If engine anti-ice is not required, takeoff is performed with engine airs and pack 1 and pack 2 selected on. If this configuration is used, cabin air must be set to recirc to minimize performance loss. Click on the yellow ellipse and set up the panel as above. That completes the pre-flight checks for the air supply system. The next section describes the in-flight checks. In flight. If engine air was not used for takeoff, it should be switched on after takeoff, and APU air switched off. When APU air is switched off, confirm that the APU valve not shut and APU non-return valve leak annunciators are out. Under normal conditions, no other changes to air supplies will be necessary in flight until the aircraft is being prepared for landing. Where possible, engine air should be used for landing to reduce APU usage. With engine air on, performance will only be limiting in conditions of high temperature and high altitude during a go-around. Engine air on is also not permitted with engine anti-ice on during a go-around. The procedure for deciding how to set up the air supplies for landing is similar to that used for takeoff. If engine anti-ice is not required during the approach and go-around, we must refer to the performance data to see if the go-around performance is limited. If performance is not limited, then engine airs and packs 1 and 2 remain on. Cabin air is selected to recirc. Click on the yellow ellipse and set up the panel as above. If engine anti-ice is required, or if performance is limited, then APU air is selected on if it is available, and engine airs are selected off. Click on the yellow ellipse and set up the panel as above. Post-flight. If the APU has not been started before landing, it may be started once the aircraft is on the ground to provide air conditioning after main engines shutdown. One minute after APU power available illuminates, APU air can be selected on. Engine air can now be selected off. If the APU is to be shut down, both packs and APU air should be selected off first. That completes the checks for the air supply system. The next section covers the abnormal operations. Overpressure or overtemperature. If the air supply temperature or pressure exceed their limits, the associated engine air valve will automatically close. This will be indicated by the engine air fault annunciator. The engine air valve annunciator will light to indicate that the valve has closed. Engine air fault will remain lit for 60 seconds after valve closure and will then extinguish automatically. The relevant engine air switch should be selected off. After 30 seconds, it may be selected on. If the engine air valve remains extinguished, the system may be used as normal. If the engine air valve remains lit, switch engine air off again and leave it off for the remainder of the flight. The remaining engines bleed air can supply the rest of the system on the affected side.